So what's the difference between a weak acid and a strong acid? Let's think about a strong acid that's pretty common, which is hydrochloric acid, and then compare that to a weak acid, which is hydrofluoric acid. When you have a strong acid, the acid will basically completely dissociate or break apart. So we'll have all of the hydrogen ions, they will separate from their chloride ions, and you'll have this happen completely. Notice how all of the hydrogen ions are separate from all of the chloride ions, 100%. So we would say that a strong acid has a 100% dissociation. So let's put that in our beaker. I do have to take a moment here to be a little bit more correct and say that there's no hydrogen ions literally just floating around freely. They're going to be complexed with water or combined with water. So here's what the equation looks like. We have HCl, we add it to some water, and what we're going to get, and we're going to use this kind of arrow because it's a strong acid, is the chloride ion and the hydronium ion, which is H3O+. This is called proton transfer. So if you were to see it like this, you have the hydrogen ion, it goes and gets attracted to the negative side of a water molecule, and that gives you the hydronium ion. I could put AQ after these because they are aqueous, but we kind of are going to need to understand that whenever you have positive and negative charges, just understand that there's going to be AQ. Sometimes they're omitted just to save room, or ink, or whatever. It's also important to recognize that since we know this occurs in water, we can kind of take the water out of the equation and simplify it a bit. So you'll oftentimes see just like HCl, and I'm going to reverse the order and put the H plus first because it doesn't really matter, but H plus and Cl minus. So effectively, the H3O plus and the H plus are like the same thing. It's just quicker to just write the H plus, even though in reality, it's going to look like H3O plus. Okay, so a strong acid is going to 100% dissociate or break apart, but what about a weak acid? I'm going to be generous here and just say and round up the percent dissociation for hydrofluoric acid, but it's actually not even this high usually. It's about 10%. So we have 10 HF molecules here. What we're going to do is we're going to break apart just one of them. So a weak acid is not going to have complete dissociation. A weak acid is going to have actually mostly, it's going to stay together as the original whatever it is. So most of them are going to be floating around as HFs. Only a few of the hydrogens are going to break free from the fluorides relative to the number that did not. So that's what makes it a weak acid. The equation works the same way. We have the hydrofluoric acid and water. Some of the fluoride ions will break off of the H ions and the H's will complex with the water, and we're going to get the hydroniums. And this is the full way. This is the shorthand way, and they effectively mean the same thing. I didn't put AQ, but you know that it could go there if you were looking at it at a traditional way. This list shows us the relatively very few strong acids, which are going to be in this section. So you have to usually memorize which acids are strong, and every other acid is going to be weak. So all these other acids are weak. But how weak? How do we know? How do we quantify or compare the weakness of an acid? How much it does or doesn't break apart? So for strong acids, the Ka is going to be extremely large. We'll talk about what a Ka is and a pKa in just a second. And the way that you're going to use those values is you can compare them to compare which acids are weaker or stronger. So we have here hydrofluoric acid. It has these two numbers, which we'll talk about. But what we can tell immediately is that this number is going to be comparable to other numbers. And we have something like acetic acid, which is in vinegar. It is even higher, which means it's an even weaker acid. So what is Ka? Ka is the acid dissociation constant. So it's capital K, lowercase a. And the way that you write the Ka, and it only really is useful, as you saw, for weak acids, the way that you write the acid dissociation constant is you look at the products, so the right side of the equation, and you put them in square brackets because we're expressing those as concentrations. So we have H plus, we have the F minus, the order does not matter. And then you put the reactants, so to speak, or the left side of the equation in the denominator, which is just HF. Now, as we saw here, most of these HFs actually stayed together and only very few of them broke apart. So since most of them, a high concentration of the HFs did not break apart, we're going to have a very large denominator. And if you think about how fractions work, a very large denominator means you're dividing by a large number, so you're going to have a small number here. A small Ka means that it is a weak acid. So let's look at our Ka values. We have some pretty tiny Kas. Notice how these Ka values get smaller and smaller as you go down this list, and this is not even the complete list, but these smaller values means that they dissociate less and less and less, so these acids as you go down this list are getting weaker and weaker and weaker. But notice how these pKa values are getting larger and larger, so let's talk about what pKa is. And these values have been researched and they are available like as literature values. So we have about 7.2 times 10 to the negative 4. There are no numbers, or there are no units, they're clearly numbers. So this is a small number. When numbers get really, really tiny or really, really big, sometimes we take the log or the negative log of that number to kind of make them more reasonable, more familiar numbers so that we don't just have a bunch of scientific notation all the time. So that's why we have the pKa. So the Ka value for hydrofluoric acid is pretty small, and they get even smaller. However, if we take the negative log, that's what P means. P means negative log of, so something definitely to know, that we have P, and it translates to the negative log of whatever is after it. So the pKa is literally just equal to the negative log of the Ka value, which is 7.2 times 10 to the negative 4. And that's going to give us a reasonable looking number of about 3.14. So how do you interpret a pKa? A pKa basically tells you how weak an acid is. So larger pKa values means that the acid is weaker. So we have increasingly large pKa values. Notice how we have increasingly small Ka values. They will go opposite directions, but that's okay. Because as you go down this list, the pKa values get larger and larger, and these acids get weaker and weaker. And effectively, remember that the Ka tells you how broken apart an acid is in water. It's weak if the Ka is really small. But since we take the negative log of the Ka, and we look at the pKa often, just because it's an easier number to think about, a larger and larger pKa means that the acid is weaker. So when will you use the pKa or the Ka? First, you got to understand how to go backwards. So mathematically, you kind of have to review your math here, but if you are given the pKa, or you'll oftentimes be given both, but if you are just given the pKa, you can mathematically go back and get the Ka. But the Ka is a constant for a particular acid at particular temperature under certain conditions. It's a literature value. Look it up in a table or in the back of a textbook, or your teacher or professor will give it to you. However, you might want to find the concentration of the hydrogen ion, because if you find the concentration of the hydrogen ion, that will help you determine the pH of the solution. But that's a different video. So what we're going to take away from this is strong acids have complete dissociation 100%. Because you're going to have such a small or non-existent denominator, their Kas will be extremely large to the point where you don't even think about it, and they're useless. But when it comes to understanding how that compares to a weak acid, that's when Ka and pKa mean something, because a weak acid will not completely dissociate. Matter of fact, a weak acid will mostly not dissociate, so you're going to have a large denominator, which means you're going to have a really small Ka value. So small it can be annoying. So to help with annoyingly small numbers, we take the negative log of that number, and that gives us a more reasonable number. Larger pKa means a weaker acid.